Welcome guys to another beautiful episode. My name is Tobile King. I want to thank Liberty for the Tenfold education app. Thank you so much for sponsoring us. I want to again say a thumbs up and a big thank you for all the questions that keep coming through. I really see how hard you guys are working and I'm really proud of you guys. So in today's lesson, I want us to look at all about the photoelectric effect. So now, before I actually start, I want to put some type of scenario in your head. So as we move along, you can actually keep referring back to the scenario. I want you to think about a table full of marbles and you have a tennis ball, right? And you want to hit those marbles so hard that the marble actually bounces off the table at a certain height. But now you can't just throw the tennis ball very little. No. You have to throw the tennis ball quite roughly so that it actually has enough energy for the marble to actually bounce and bounce up, right? So this means you need a certain frequency, when we talk about the photoelectric effect, that can actually emit an electron on a metal surface. So now all the electrons, they don't just get emitted. We need a certain amount of light. Like you also need a certain amount of strength to actually throw that tennis ball to actually move the marble. So the electrons are exactly the same way. Now we know that metals are very different, even the intermolecular forces between them. So you need a certain different types of light with high frequencies that can then actually emit those electrons. But now when you have this light that's coming through and it wants to emit this electron, it can't just come to the electron and then it has emitted it. No, these electrons are very spoiled brats. It should actually emit the electron so that it has enough kinetic energy, right? So it can be emitted and then it can actually start floating. So now remember, when we have let's say per rate of time, a number of electrons that are being emitted, we then can calculate or have current. So I want you to think of it like this. When you ask for tuck shop money and you ask your mommy for 10 Rand, you don't even want 10 Rand on a Friday, you want 50 Rand because you want to have enough money to spoil yourself as well. So the electrons are exactly the same way. They want enough kinetic energy to be emitted from the metal surface, but also have enough energy to actually start moving around. Because if they do not have this kinetic energy, then they cannot move. So the photon that actually comes and emits them needs to have enough frequency to emit it and give it kinetic energy so that it can start moving. So now this means you'll have a minimum amount of frequency, you have a minimum amount of the work threshold and so forth. So those are the terminologies we're thinking about. But I want you to think about you need to have a certain frequency, a certain amount of strength to actually move the marble or to emit the electrons. So without wasting time, let's start with today's question. So the first question that I have is from Vutiva Masekane. And I hope it's a he gave us a question. And the question reads, in an excited atom, now remember, if something is excited, it's got some energy. So in an excited atom, electrons can jump from a lower energy level to a higher energy level. But now remember, if electrons do not have enough kinetic energy, then they're not able to jump from one energy level to another energy level. So they need to have enough or take in enough kinetic energy, and then they're able to move. It's the same as you. Before you run a race, you warm up, get your blood pumping and all that stuff, and then you get excited, and then you're able to run the race. You can't wake up and then you start running the race. No. You must first get excited, rejuvenate yourself, and then you are able to run. So electrons are exactly the same way. So they are able to jump from a lower energy level to a higher energy level. They can also drop from a high energy level to low energy levels. Now they've given us a diagram and it says in the diagram below, not drawn to scale, it shows some of the transitions. Remember, transitions just means change for the electrons in an excited state. Now guys, something that you need to, I feel like I keep saying it in terms of physics and chemistry, if you are given a table or you're given a diagram, a picture and so forth, and they say use the graph or the diagram below, make sure all your information comes from the diagram below. The examiners are trying to see whether you are able to analyze the diagram given and then you're able to actually maneuver around and find your answers. So don't go bring in something that's not there. Always try to see first, can you find all your information from this graph? So here what I see is that I've got increasing energy going up, which is true, because if an electron moves from energy level 2 to energy level 3 to energy level 4, it needs an increase in energy. On the right-hand side, we have the different energies that are given here. So this will be for level 4, level 3, and level 2. And as you can see, the numbers keep getting higher as we move up to the next energy level. Let's look at the first question. Number 11.2.1 says, do the transitions indicated in the diagram lead to absorption or emission spectra. Now remember, we've got an increasing energy and the electrons are excited. That's your term. Excited means they are moving up energy levels. Remember in grade 10, we were taught that this is the ground state. This is the ground state of electrons. So they move from a ground state moving all the way up and the energy levels keep increasing. So this will then be the emission spectrum because it's actually moving up. So let's answer that one. So this is 11.2.1 and this is the emission spectrum. This is the emission spectrum. So I'm going to write the next numbering for the other one, 2.2. Let's see what the next question says. So the next one says, number 11.2.2 says we need to calculate the frequency. Now remember, we know that frequency is an F of the photon produced when an electron in an excited atom makes a transition from E4 to E2. Now remember, the word transition means change. So now I can see E4 and E2. I can see I'm going to use E4 and E2. So when they say transition, that means there must be a change in something. I want to take you back a little bit. When we were doing momentum, vertical, projectile motion, we had final velocity, we had initial velocity. So we were able to determine that the car was driving and its final velocity was so much, and the initial velocity was so much, we were able to calculate acceleration, or it doesn't matter what, but we had a change in velocity. Now the same thing with the electron. It had a certain energy level in the second energy level. It had a different energy on the fourth energy level. We must find the change between the two. Now, going back to momentum, to find the change in those velocities and so forth, we would always say final velocity minus initial velocity. So we're doing exactly the same way. Remember, this is laws of mathematics. So we're just going to do exactly the same way. We're going to calculate this one here, subtract this one here, and then we'll be able to find the change in energy. And once finding the change in energy, we are then able to find the frequency. So let's see how we're going to do that. So for the first one, remember we moved E4 was my highest energy level, and we have E2, which was my starting energy level. It's exactly the same. This will be V final if we were doing vertical projectile motion or momentum, and this will be VI or initial velocity. So the initial one, we had 2.044 times 10 to the negative 18 minus, let me just check what the second one was. We have 1.635, okay. So we have 1.635 times 10 to the negative 18. Let me see, let me calculate this. Oopsie daisy. Okay, let's go find a calculator. Okay, there we are. Oopsie daisy, there we are. Yay, killed it. Okay, now put this in brackets. We're going to have 2.044 multiplied by 10 to the exponent negative 18, close my bracket, minus 1.635 times 10 to the exponent negative 18. Then I get 4.09 times 10 to the 19. So I get 4.09 times 10 to the negative 19. Remember, when we're talking about energy, it needs an SI unit, which is joules. And guys, remember, for everything that we actually calculate in physical sciences, you need to have an SI unit. Remember, we also deal with scalars or vectors, so some have magnitude and direction, and some only have magnitude. But you have to indicate to the examiner that you know that energy is measured in joules. So you also don't want to be penalized if you do not put the joules. But that is then the case. We found our energy. So this is the change in the energy for that photon that was emitted. But they wanted us to calculate the frequency. So the next thing I know, from my formula sheet, I've got E is equal to HF, E being my energy, H is Planck's constant, and F is the frequency that is required. So I'm just going to work backwards. I'm going to put this number for my energy. So I'm going to say 4.09 times 10 to the negative 19. Always remember to write the formula because you get a mark for that. H is a constant, but you'll get this on your formula sheet or you know it off by head. So it's 6.63 times 10 to the negative 34, but I'm looking for my frequency. Now, mathematics. If I want my F to be alone, I'm going to divide both sides with what is bothering my F. So that will be 6.63 times 10 to the negative 34. I'm going to do that on both sides, times 10 to the negative 34. This and this will cancel, or rather gives us 1. So now let's find what my value for F is. Oopsie daisy. Okay, there we are. So I'm going to use this side. I'm just going to put it exactly as it is in my answer sheet. Let's see. I'm going to put this side on my calculator exactly as it is. So I'm going to have 4.09 times 10 to the exponent negative 19. Bring that down. On this side, I'm going to have 6.63 times 10 to the exponent negative 34. Remember, this is Planck's constant. And then for my frequency, I get 6.61. Now remember, the 8 is going to turn the 6 into the 2 because we are rounding off to 2 decimal places. And this will be times 10 to the negative 14. So my frequency will be 6.17 times 10 to the 14. Remember, the SI unit for frequency is hertz. So the only tricky part about this question, you first had to find the change in energy, and then this it's easy, you find on your formula sheet. But this is what we'll then get, the frequency for the excited photon. So let's look at the other question. So now we're going to some little bit of information first here. It says the threshold frequency. Remember, when we talk about threshold, it is the minimum amount, the minimum energy required for radiation. So the threshold frequency of a metal, which they call Q, is 4.4 times 10 to the 14 hertz. Okay, so that is FO. We've given a little bit of information here. And then 11.2.3 says we mean to calculate the kinetic energy. Now we know when we're looking for kinetic energy, we say EK, of the most energetic electron ejected when the photon produced in this question. So we have to use the frequency used here to calculate the kinetic energy because they're looking for the most energetic that we've got in 11.2.2 is the incident of the surface of metal Q. So now something interesting, remember, if for example in the previous question your frequency was incorrect, but you are substituting it again in 11.2.3, you do get it right for continuous assessment because you actually substituted right. So even though it is wrong, you will get a mark for actually substituting correct. But let's not try to get it wrong because we are actually trying to get full marks for this question. So now we need to calculate the kinetic energy, and that we already calculated the frequency in the previous question. So let's see how we're going to do that one. So that is 11.2.3. So now looking at my formula sheet, I know I'm looking for EK, but in the previous question, I was given energy. And then remember, energy is equal to HFO, but I can also find EK because remember, I am looking for my kinetic energy. So this is a formula that I'm given. Now I need to start plugging in what I have and then leave out what I'm looking for. So this is what you get on your formula sheet. So now let's see what I do have and what I'm actually looking for. So what I do have, the energy from that photon, we calculated in the previous question. We got 4.09 times 10 to the negative 19. That was my energy. H is a constant. It is Planck's constant, which is 6.63 times 10 to the negative 34 times 10 to the negative 34. And then we calculated our frequency. The frequency that we didn't calculate it, we are given the frequency. They are told us that the frequency for this photon, there we have the threshold frequency is 4.4 times 10 to the 14. So I'm going to put it there because that is my threshold frequency. That is 4.4 times 10 to the 14 hertz. But the question says I'm looking for my EK max. I'm looking for my kinetic energy. So now it's just mathematics. So I'm going to make EK the subject of the formula. So I'm going to move it to this side of my formula sheet of my equation, EK max. I'm going to leave this on that side. So I'm going to have 4.09 times 10 to the negative 19. Remember, this is multiplication, so I'm going to move everything on this side. But remember, if something jumps the equation sign, the sign changes into a negative. So then I'm going to have 6.63 times 10 to the negative 34, which is multiplied by the threshold frequency that we were given, which is 4.4 times 10 to the 14. Close my brackets. So now let's put this in our calculator and see what we are getting. put it exactly as it is. Now remember to always put brackets around your stuff because you don't want to also get the wrong answer. So I have 4.09 multiplied by 10 to the exponent negative 19. Close my bracket. Now minus, I'm going to open a bracket. Then I'm going to put two brackets so that it looks like this. 6.63 times 10 to the exponent negative 34. I'm going to close my bracket. Remember, it's multiplied by 4.4 times 10 to the exponent 14. Close my bracket, and then this is the answer that I get. I'm going to round this off to 2 decimal places. Anything greater than 5 or 5 will change the next number. 2 is too little to actually change the 7, so it's going to remain 1.17 times 10 to the negative 19. Always make sure that you leave it in 2 decimal places unless stated otherwise. So my kinetic energy for the most excited electron is 1.17 times 10 to the negative 19. Remember, when we are talking about energy, we are talking about the SI unit of it being in joules. Okay, let's see. Now we are moving to another question. Let's see what it says now. So we've calculated this one, and then they're telling us we have another metal, which is R, and this metal has a threshold frequency of 7.5 times 10 to the negative 14. Now remember that all metals will not have the same threshold because remember, not all metals are the same. The intermolecular forces are also not the same, so different metals might require then different thresholds. So in this case, they're giving us R, and as you can see, we've got a different threshold. And the question says, will the photon produced in 11.2.2 be able to eject electrons from the surface of metal R? And we must write down only yes or a no. Now remember, how do we need to know this? You have to look at the frequency that you were given here, and you have to find the frequency that you were given here. So let's write our final answer. So in this case, because the two frequencies were not the same, that means our answer is going to be a no. And how do I know this? I'm going to show you how you actually elaborate your answer like this, and then I'm going to explain to you. Remember, if you have the threshold frequency, let me just add on to something. If they say yes or no and give a reason to your answer, don't say because the paper says so or because it's written on the exam paper. No, the examiner wants to see whether you understand that when we have something with a high threshold and when we have another metal with a low threshold, there's actually a difference with the electrons that are going to be emitted or ejected and the kinetic energy that they're going to have. So when you are given a statement where they say explain, you must then use the two to say no. This one is higher because of this, and this one is lower because of this and this. And you are showing the examiner whether you know the correlation between the two. So I'm going to write a statement. I'm also going to write a formula that's going to help you understand where does it actually come from. I want to take you back a little bit. When we do vectors and so forth, we usually say something is directly proportional to something or something is inversely proportional to something, and that is then how we elaborate our answer. So it's the same thing when you come to photoelectric effect. You can actually use your formulas to actually help you elaborate your answers. But in this case, I can first say, I think I have 2 ways to actually write it. So I can say, no, the frequency, the threshold frequency, let me skip steps. We have the threshold frequency. Remember, threshold is the minimum energy required for radiation. Frequency, minimum frequency, the threshold frequency is greater than the frequency, of the photon. So the minimum amount of energy that is required is actually greater than the frequency of the photon. So that photon's not going to have much. And how do I know this? Remember, we have 7.5 times 10 to the 14 hertz. I can see that the threshold is greater because the photon actually is 6.17 times 10 to the 14. And this is what we've calculated. But then you can also say, let me just make a dot here. But you can also say the frequency, can say the frequency of the photon, and remember this was going for 2 marks, of the photon is less. This is how you show something is or is not. The photon is less than the threshold frequency. Threshold Tenfold frequency. And how are you going to show this? We're just going to do this part here the other way around. So I can then say 6.17 times 10 to the 14 is smaller than 7.5 times 10 to the 14, and that's both hertz. So now, by you doing this, you are showing the examiner that the photon has got less energy than the energy that is actually required to actually emit the electron. So even though the photon gets there, it doesn't actually meet the requirements. It's like going to a tuck shop and you only have 6 rand, but the pie is actually 8 rand. You don't actually meet the requirements that are actually required there. So you are showing the examiner that you understand that when a photon is actually moving, and then the minimum energy that is required should actually be different, or it should then be more. So when you're doing this, you are showing the examiner that it works. So remember, this was only for 2 marks, so you actually get an answer for saying yes or no, and then you get an answer for explaining. Remember, do not just say because the paper says so. Show the examiner where you're getting your answer.